I welcome you all for this lecture series. See the graded architecture, that means long short term memory, LSTM. And first we should know why we are going for this LSTM, long short term memory. This long short term memory, LSTM, is a special type of recurrent neural network, RNN, designed to learn from the sequence data while solving the major problems of traditional RNNs. The vanishing gradient, where older information fades away as new data comes in. LSTM introduces a gated architecture. A gated architecture means the input gate, for get gate, and output gate that carefully controls what information to keep, update, or discard from memory over time. This allows the network to remember important patterns for long durations, making it powerful for tasks where context matters, such as speech recognition, language translation, handwriting predictions, ECG signal analysis, and serious forecasting. We learn LSTM because many real world problems involve sequential data with long term dependencies, and LSTM provides a reliable way to model how past informations influence future outcomes. This we are going to see it in detail. We'll see one by one. First, the traditional recurrent neural networks. What is the problem with the traditional neural networks? The traditional neural networks are designed to process sequence by passing information from one time step to the next through hidden states. In theory, this structure should allow them to remember earlier inputs. That means earlier input means the past inputs. So they should remember the past inputs and use them later. However, during training, RNN use back propagation through time, and the gradients which carry learning signals get multiplied repeatedly. When these gradients are less than 1, what will happen mean they shrink exponentially as they move backward in time. This causes the vanishing gradient problem, and which will create the vanishing gradient problem, where earlier time step receives almost no learning. What will happen means no learning signal receives the almost no learning signal. As a result, the model forgets information from the distant past and mainly relies on recent inputs, which limits its ability to model long-term dependencies. Example of RNN limitations are, for example, in the sentence "the movie," which I was watched last year, was amazing. The keyword "movie." What is the keyword here? Movie is the keyword. Appears early than the keyword movie appears far earlier than phrase was amazing, which describes it. A simple RNN must carry the meaning of movie across many intermediate words. Due to vanishing gradient, the memory of movie weakens as the sequence progresses. By the time the network reaches was amazing, it may no longer strongly associates this phrase with movie. Therefore, the RNN struggles the capture a long distance relationship in language which are common in real world text. Then why we should go for this need for long term memory? Many real world problems such as language translation, language translation, speech recognition, ECG signal analysis, and time series forecasting depends on information that appear much earlier in the sequence. Standard RNN have short-term memory because their hidden state changes too much at each step and older information fades quickly. This makes them unsuitable for tasks where context from far back is important. Hence, a new architecture is needed that can retain information for long durations while still updating with the new inputs. So, we are going for this. So, LSTM solves this using by memory or cell. Long short-term memory cell network introduces special structure called memory cell. It will introduce as the memory cell, which stores information separately from the main hidden state. This cell is controlled by gates that decide what to keep, update, or remove. Unlike RNN hidden states that overwrite information at every step, the memory cell allows important data to stay unchanged over many time steps. This makes LSTM capable of preserving long term information while still processing new inputs efficiently. Next, cell state, long term memory cells. The cell state is here is the core of LSTM across acts as a highway for information flow across time steps. Here, information moves through this path with only smaller lines interacts instead of repeated nonlinear transformations. Here, the forget gate is it removes the useless information, input stores important new information, and output gate decides what to send forward. The structure helps preserve important context and reduces vanishing gradient issue, making long-term learning possible. This cell behave here it prevents the vanishing gradient. The cell state behaves like a conveyor belt where information traveled. Uh, where information travels forward almost unchanged unless gate modify it. This design ensures this design ensures that the relevant past information is continuously available to future steps. Only selected parts are added or removed, preventing unnecessary distortion of stored memory. This controlled flow is key to maintaining stability in learning long sequences, and it prevents a gradient from the shrinking too fast. Since the cell state allows most linear update, gradient flowing backward during training do not repeatedly pass through shrinking nonlinear functions. Instead, they can move along the cell state path with a less decay. This directly addresses the vanishing gradient problem and enables the network to learn dependencies over long time spans. So it has been given by Ct is equal to Ft Ct minus 1 plus It into Ct. The gradient can flow through many time steps without disappearing. Next, gradient mechanism is equal to, we can call it as intelligent control. So long-term memory, the long LSTM, long dependency, LSTM uses a gating mechanism to regulate information flow. Gates are neural network layers with a sigmoid activation function. Here, sigmoid activation functions producing value between 0 and 1. A value near 0 means block information, a 1 means allow information. The near 1 means it allows the information. The gates act like decision makers, determining what to remember and what to forget and what to output, making the LSTM a highly controlled memory. So here there are three types of gates are available. The three gates are forget gate, input gate, and output gate. As I've said, the forget gate removes irrelevant information from the cell state. Input gate adds new useful information, and output gate decides what part of the memory should influence the hidden state and the final state. Together, these three gates, manage the memory efficiency, manage the memory in an effective way. And LSTM acts as a smart memory system because of its gating and memory cell structure. LSTM behaves like a smart system where selectively keeps important data. This will maintain the important data and discards noise. It does not blindly store all past information, but instead learned what is relevant for task. This makes it much more efficient than a simple RNN in handling complex sequences. And it prevents the vanishing gradient. As I've said, the cell state updates equation allows the gradient to flow backward through, see here, Ct minus 1. Many time steps with minimal multiplication by small numbers. This preserves a learning signal from distance time step. Thus, LSTM can learn a relationship that span long intervals, which is difficult for a standard RNNs. Learns long-term dependencies. LSTM can connect events that are far apart, that is far apart in sequence. In language, it links words separated by many others. In signals, it captures patterns across long durations. In time series data, what it will do is it models trends spanning many steps. This ability to learn long term dependencies makes LSTM suitable for complex sequential problems. And what is the practical impact of this LSTM? The LSTM became a foundational model in deep learning before transformation emerged. It powered early NLPs, NLP systems like language modeling and translation, speech recognition system, medical signal analysis such as ECG and EEG interpretation, and financial time series forecasting, etc. Its ability to maintain memory over long sequence made it highly successful in real world applications. So finally, we use LSTM because standard RNN forget information too quickly due to vanishing gradient. LSTM overcomes this by using memory cell and gating mechanism that allow important information to be stored and controlled over long sequences. This makes LSTM effective for tasks that require understanding long-term context. Coming into the figure, this is the problems with the traditional RNN. So it will what are all the problem? Vanishing gradient problem, forget long term information and cannot remember the past information. This could be overcome by using this long short memory cell. This image explains why LSTM is needed by comparing the limitations of ordinary limitations of traditional RNN with the advantages of LSTM. On one side, it highlights that the standard RNNs suffer from vanishing gradient problems, causing them to forget earlier information as sequence becomes longer. This makes them poor at handling long-term dependencies. On the other hand, this image shows that LSTM overcomes this issue using a special memory structure called the cell state and three gates. What are all the three gates I have said? A forget gate, input gate, and output gate. This is very, very important, these 3 points. Forget, input, and output. The control and that control the flow of information. These gates allow LSTM to keep important data, remove irrelevant information, and pass useless memory forward. Overall, this diagram conveys that LSTM acts as an intelligent memory system capable of learning long-term patterns effectively. So simply we can say keep important data and it will drop the rest. So hope everyone understood the difference between the problem with the traditional RNN and the solution. These problems will be overcome by using this structure. The structure is known as long short-term memory. Hope everyone understood this concept of LSTM. The remaining things we'll discuss in the next lecture. Thank you.